cosine of z equals negative 2i. So z is our complex variable. Z is equal to x plus iy. And then the cosine of x plus iy is equal to the cosine of x times the hyperbolic cosine of y minus I times the sine of x times the hyperbolic sine of y. So the real part is cosine x, hyperbolic cosine y, and the imaginary part is negative sine x, hyperbolic sine y. So if we would like to solve the equation cosine of z equals negative 2i, then we have to consider the real and imaginary parts of the number negative 2i. That's 0 minus 2i. So the real part is 0, and the imaginary part is negative 2. So the real part of cosine z has to equal 0, and the real part of cosine z is cosine x times hyperbolic sine of y. That has to be 0, and at the same time, the imaginary part of cosine z has to equal negative 2, which means that negative sine x hyperbolic sine y has to equal negative 2. And of course we can multiply through by the negative here. But we have to find x and y, all x and y, which solve both of these equations simultaneously. It's a good idea to start with the equation that has a 0 on the right side, because if the product of two quantities is 0, then one of the quantities must be 0. So this equation boils down to either cosine of x is equal to 0 or hyperbolic cosine of y is equal to 0. Now the cosine of x is equal to 0. On the unit circle, the cosine is 0 at the top and the bottom. That's pi over 2, and negative pi over 2 is one way to look at it. But we want to consider all of the infinitely many solutions. So x is equal to pi over 2 plus k pi, where k is an integer. Here's pi over 2 at the top. Pi over 2 plus pi is at the bottom. Pi over 2 plus 2 pi is at the top again. Pi over 2 minus pi is at the bottom. Pi over 2 minus 2 pi is at the top again. Okay, so that's when cosine of x is equal to 0. Cosh y, hyperbolic cosine of y, equals 0. That means e to the y plus e to the minus y over 2 is equal to 0. There's no solution to this equation because the exponential functions here are both positive. So there's no solution here. The hyperbolic cosine function has a minimum of 1 at 0. So the cosh 0 is 1, and that's the minimum value of the hyperbolic cosine. Okay, so the first equation here, cosine x times hyperbolic cosine of y equals 0, tells us that x has to be of this form, and it gives us no information at all about y. So let's put that in our pocket and move over here. Now, when we look at this equation, we can keep in mind the value of the x. So let's transfer that here. if x is equal to pi over 2 plus k pi, then that means that the sine of x is either plus 1 if the angle is at the top, or minus 1 if the angle is at the bottom. So the sine of x will equal 1 if this value of k here is even, like 0 or 2 or negative 2. And the sine of x will equal minus 1 if k is odd. That will put us down at the bottom. Okay, so let's start with, we have x equals pi over 2 plus k pi, and let's suppose that k is even. That means that the sine of x is equal to 1, and that means that the hyperbolic sine of y has to be 2, because negative 2 equals negative 2. We're putting a 1 in here. So the negatives cancel, and we get hyperbolic sine of y equals 2. So we have to solve this equation for y. So hyperbolic sine of y is equal to 2. That gives us e to the y minus. The hyperbolic sign has a minus e to the minus y over 2 is equal to 2. Solve for y, multiply both sides by 2. E to the y minus e to the negative y is equal to 4. Now multiply both sides by e to the y. E to the y times itself, you add the exponents, y plus y. E to the y times e to the negative y, you add the exponents, you get e to the 0, which is 1. And then 4 e to the y. So this is e to the 2y minus 4 e to the y minus 1 is equal to 0. Now we're going to let u equal e to the y. So this one is u squared, e to the y quantity squared, multiply the exponents. You get 2y for the exponent. This is u, 4u, minus 1 is equal to 0. Here's a quadratic that does not factor, and so u is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a, using the quadratic formula there. The b itself is negative 4, so negative b is 4 plus or minus b squared, which is, the square root of b squared, which is 16, minus 4ac. For a is 1, and c is negative 1. So this is minus negative 4, which is plus 4, and divided by 2a, a is 1. So we get 4 plus or minus the square root of 20 over 2. And now let's simplify that. U is equal to, we'll divide the 2 in here, and we get 2 plus or minus the square root of. If we divide the 2 in here, then we have to think of the 2 as being the square root of 4, and then we get the square root of 5 altogether, 20 divided by 4. So u is 2 plus or minus the square root of 5. Notice that the square root of 5 is more than 2, because here we had 16, which the square root is 4, and then we added to it, so our discriminant here is larger than 4 squared. So if 2 minus the square root of 5 will be negative. So let's just keep that in mind here. 2 minus the square root of 5 is negative. So u was e to the y. So e to the y is equal to 2 plus or minus the square root of 5. But e to the y is positive for all y, real numbers. Y is a real number. So for any real number, e to the power y is positive. So e to the y equals 2 minus the square root of 5 has no solutions. And so that means we only have to consider e to the y equals 2 plus the square root of 5. And that means that y is the natural log of 2 plus the square root of 5. Okay, so this gives us some solutions to the equation. If cosine of z is equal to negative 2i, then so far we have x equals pi over 2 plus k pi, where k is even, and y is the log of 2 plus the square root of 5. So that our z, which is x plus iy, has the form pi over 2 plus k pi, k even, as the real part, plus I times the log of 2 plus root 5. Now we still have the other consideration. Let's go back to that. We had sine of x, and we were looking at this equation here, this one here, negative sine x times hyperbolic sine y equals negative 2. And we considered the possibility that sine x was equal to 1. So now we have to consider the possibility that sine x is equal to negative 1. So now we want to do, so let's write that equation down again here. It was sine x times hyperbolic sine of y equals 2. I removed the minus signs. And now we're saying if x equals pi over 2 plus k pi, where k is odd, then on the unit circle, that's the point down here, so that the sign is negative 1. So that means that the hyperbolic sine of y has to equal negative 2, because negative 1 times negative 2 is the only way to get it 2 here. We know that the sign is negative 1. So negative 2. And now we follow the same method that we did just a moment ago. In fact, if we change this 2 into a negative 2, how does that change all of this work that was here? If this was a negative 2, then this would be a negative 4. And so this would be a positive 4, which would change this to a negative, but it wouldn't change this. So it would change this one to a negative, but it wouldn't change this one because we were squaring the b. So we would get u equals negative 2 plus or minus root 5. So u equals negative 2 plus or minus root 5. Solving this equation again the exact same way we solved the last one. And u was e to the y. Negative 2 plus or minus the square root of 5. Now e to the y has to be positive, so e to the y is not going to equal negative 2 minus root 5. That's going to have no solution. So we have to have e to the y equals negative 2 plus root 5. This is a positive number, and so y is the natural log of negative 2 plus root 5. So our z in this case is x plus iy, and the x is pi over 2 plus k pi, where the k is odd, and the y is log of negative 2 plus root 5. K is odd. So all of our solutions together, if we just take these and put them together, then that's all solutions. So what do we have all together? We have z equals x plus iy, where x equals pi over 2 plus k pi plus I ln 2 plus root 5. And here we have k is even, or I should have just, let's see, I said x equals this. I just gave you everything here. So this is z equals, or z equals pi over 2 plus k pi plus I log negative 2 plus root 5, where k is odd. So we have infinitely many solutions, and we have slightly different imaginary parts depending on whether k is even or odd. If k is even, then we have a positive 2 here in our logarithm. And if k is odd, we have a negative 2. And they both have this root 5 here. Okay, so we have infinitely many solutions to the equation cosine of z equals negative 2i.